Example number 1, state the area of a circle and then find DADR when R is equal to 3 inches. Give units in your answer. So what is the area of a circle? We're off to a roaring start so far. Area equals pi r squared. And so DADR would be the derivative with respect to the radius. So the derivative of A with respect to the radius is going to be DADR. And then I need to take the derivative of pi r squared. So I'm going to do the product rule. I've got pi times the derivative of r squared. Derivative of r squared is 2r. And they want me to evaluate this when the radius is equal to 3 inches, okay? So I'm gonna write it in this notation. I've got DADR of 3. And so I take 3 and plug it in. So that would give me 6 pi. And let's not do something careless like leave off the units, right? When they say to include the units. And so the area is measured in inches squared. I ran out of room there, so inches squared. And then my radius, it's dA over dr, right? So I've got the units for the area over the units for the radius, and the radius is measured also in inches. So it's inches squared per inches, meaning that if I increase the radius, the area will increase in square inches there. If I increase the radius in inches or decrease it, right? So 6 pi inches squared per inches. So far, so good. Example 2, state the volume of a cube in terms of side S and then find the instantaneous rate of change of volume when S is equal to 2 feet. Give units in your answer. Okay, so what is the volume of a cube? Zach with the formula orate. Volume is equal to S cubed. So I'm going to take the derivative with respect to the side. So I've got dV ds. That's equal to the derivative of S cubed, which is 3s squared. And I want to evaluate it. dV ds when S is equal to 2. So if I take 2 and plug it in, I have 2 squared times 3, which is 12. And let's put the units on there. The volume is measured in cubic feet, so feet cubed. And then the side is measured in feet. So I get 12 cubic feet per foot. Okay, so let's think about a little birthday party here. Newhouse is blowing up balloons for his little daughter's birthday. So I have a balloon. I'm blowing up the balloon. Tell me some things that are changing. So for example, the radius of the balloon is changing as I blow it up and increase the radius there. What else would be changing? Volume. The volume is changing. What else? Oh, the surface area is also changing. Well, the question that I have is there a factor? Is there a factor that influenced influenced all rates changing? And the answer to that is yes, there is. And that factor is time. Which gets to the main part of related rates. When we are working related rates problems, we are looking at rates of change with respect to time. So as I blow up the balloon, the radius is changing with respect to time. The volume is also changing with respect to time. And the surface area is changing with respect to time. So you do not have to write this down, but let's do a quick little review over implicit differentiation. Oh yes, so let's say I've got y cubed equals 2x plus 2y. And I wanted to take the derivative. The derivative of y cubed is 3y squared, and then I got to tag it, right? dy dx. And then the derivative of 2x is 2, and the derivative of 2y would be 2 dy dx. So when we did implicit differentiation, we learned that anytime we took the derivative of a y variable, we had to tag it with a dy dx because we are taking the derivative of y with respect to x. Okay, well, I've got some good news for you. When we are taking the derivative with respect to time, it's kind of like implicit differentiation. We've got to tag our variables, but we have to tag every variable that is changing with respect to time. Don't forget to tag, and that's the whole key to related rates. We've got to tag our variables. Okay, so let's look at an example. It says the radius and the volume of a sphere, I should have asked Zach if he knew that one, right? Are differentiable functions of time. Write an equation that relates dv dt to dr dt. So I have volume equals 4/3 pi r cubed. And I'm going to take the derivative of this with respect to time. In other words, this is like my balloon analogy. I'm blowing up the balloon, and let's assume that it's a sphere, and the volume is changing at a certain rate. Okay, so when I take the derivative of the volume here, the derivative of v would be 1, and then I got to tag it dv dt because the volume is changing with respect to time. And so this dv dt means the rate of change of the volume with respect to time. So now I'm going to do the product rule here. I'm going to make 4/3 pi my first term and r cubed my second. So I've got 4/3 pi times the derivative of r cubed. And the derivative of r cubed is it's 3r squared, and then we tag it, dr dt. Okay, because the radius is also changing with respect to time. So here's the key to related rates. We have to tag every variable when we take the derivative with respect to time, unless, with the possible exception that the variable is not changing. If the variable is constant, then the rate of change is 0 and the derivative is 0. And we don't have to tag it because it's 0. But any other variable that is changing, we have to tag it with a dr dt or a dv dt or a da dt or something like that, whatever the respective variable is. Okay, so let me clean this up a little bit. My 3's are going to cancel here. And so I've got dv dt equals 4 pi r squared dr dt. I did. Oh, sorry. So I left it off, but when I do the product rule here, The second part of the product rule is 0 because 4/3 pi is a constant. Okay. I think I skipped over that part, but it is 0 because 4/3 pi is, the derivative of 4/3 pi is constant. Okay, so questions about that one? Let's look at part B. The variables x and y are both differentiable functions of t and are related by the equation y is equal to x squared plus 3. Write an equation that relates dy dt with dx dt. So I need to take the derivative of this. I've got y is equal to x squared plus 3, and x and y are functions of t. So when I take the derivative of y, I've got 1 dy dt. Derivative of x squared would be 2x dx dt. And then the derivative of 3 is just 0. And that's it. I'm done. So I'm going to move on to the next one. It says the base and height of a right triangle are differentiable functions of t. Write an equation that relates the rate of change of the area of the triangle with the rate of change of the base and the height. So I need an area of a triangle. So area is 1/2 the base times the height, and they are b and h are differentiable functions of t. So I'm going to take the derivative. Derivative of a is just going to be 1 dA dt. And then I need to differentiate on the right side here. And so I have 1/2 b times h. So I'm going to do the product rule where my first term is 1/2 b. So I've got 1/2 b times the derivative of h. And the derivative of h is dh dt, 1 dh dt, plus h times the derivative of 1/2 b, and the derivative of 1/2 b is going to be 1/2 db dt. So I've tagged my variables when I took the derivative. I can clean this up a little bit. I could write this as dA dt equals, both of these terms have a 1/2, so I could factor that out. You don't have to do this, but I could clean it up a little bit. So I've got b times dh dt plus h times db dt. So all I've done here is factor out a 1/2. However, the second part of this says, would you do anything differently if either the base or the height was constant? And the answer to that is yes. So let's look at that. Let's say that b is constant. So if that's the case, the derivative of the area is going to be dA dt still. And then this first part is not going to change. I'm going to have 1/2 b times the derivative of h. And so that is going to be 1/2 b dh dt. But then the second part of this will change because I have h times the derivative of 1/2 b. And the derivative of 1/2 b in this case is 0 because b is constant and there is no rate of change. And so if there is no rate of change, my derivative is 0. And so I would just be left with 1/2 b dh dt. So up until this point, I mean, we sort of have done some math, but not really. We haven't put any numbers in, which we're about to do. So let's pause here for just a second, make sure everybody is on the calculus rocket ship headed for planet Newhouse, right? So are we good? So far, so good. Well, Related rates are fairly common on the AP exam. And as a general rule, the free response question, if you get a related rates, the mean is usually fairly low, which means that students find them somewhat difficult. However, we've developed a process. There's certain steps that I want you to go through where you are working these. And like I said, we're doing some of the easy ones today, and we will look at some more complicated ones on Monday. But here's the process. Step number 1, write down what you know. Step number 2, write down what you are trying to find. Step 3, draw a picture. That might be helpful in some instances, not always, but sometimes. And step 4, write down an equation that relates all of the variables involved and relates the related rates, the derivative. And here's a word of caution. We do not, quote, freeze the picture until after differentiating. Keep variables as variables until after differentiating, but constants may be put in immediately. That means we do not plug in the values until after we take the derivative, unless it's a constant. And then it doesn't matter because it's a constant and it's not changing. But if we have a variable that is changing with respect to time, we must take the derivative first before we plug in the values. Okay, so here we go. Let's look at a couple examples. Example 4. The area of a circle is increasing at 6 inches squared per second. How fast is the radius changing if r is equal to 3? So step number 1 is to write down what we know. They give me this 6 inches squared per second. What is that? It's what type of rate? It's the rate of change of what? Of the area, right? So this is dA dt because it is the rate of change of the area with respect to time. So I know that dA dt is equal to 6. What else do I know? I know that r is equal to 3. What am I trying to find? How fast is the radius changing? So that would be a rate of change. It's a derivative with respect to time. So I want to find dr dt. A picture is probably not that helpful in this instance, but okay, I got a circle. Circle is expanding. All right, something like that. My equation is just going to be the area of the circle. So area is equal to pi r squared. And now I need to take the derivative. So let's differentiate. A equals pi r squared. The derivative of A with respect to time is dA dt. Here I'm going to do the product rule. So I have pi times the derivative of r squared. And the derivative of r squared is 2r dr dt. And the second part of the product rule, again, is 0, because pi is a constant. So technically, there's a plus 0 there. Now that I've taken the derivative, I can plug in the values that I know. So what is dA dt? 6 equals pi times 2 times r, which is 3, times dr dt, which is what I'm trying to find. And so now I'm going to solve for dr dt. So dr dt, I've got 6 is equal to 6 pi dr dt. I divide by 6 pi on both sides. So dr dt is equal to 6 over 6 pi. And that is measured in, the radius is measured in inches. Time is measured in seconds. And also, if this were a calculator, You can write that as a decimal, which would be 0.318 inches per second.
Can you do 1 over 5?
Sure, same thing. That's fine. Okay, and that's a related rate, albeit a very straightforward and simple one. Any questions? Well, we're just going to look at one more. So let's look at example 5 here. 2 cars are approaching an intersection along straight highways that cross at right angles. Car A moving at 36 miles per hour and car B at 50 miles per hour. At what rate is the straight line distance between the cars changing when car A is 5 miles and car B is 12 miles from the intersection? So first step, we're going to write down what we know. And for simplicity, I call this X and this Y. It actually doesn't matter, just as long as you're consistent with your variables. I mean, you could call it A and B or whatever, but I'm going to call this is the horizontal line. So I'm going to call this X and the vertical line Y. So tell me one thing that I know. It says that car A is moving at 36 miles per hour. And so that is a rate of change with respect to time. And I've labeled the side that car A is on X. So one thing I know is that dx dt is equal to, oh, but it's not 36. Why is it not 36? Well, because velocity shows speed and direction. So it's not positive 36, it is negative 36 because car A is moving in which direction? To the left. And so by that rationale, is that a word? That came out wrong. So by that reasoning, dy dt is going to be the rate of change of car B. And so it is going to be negative 50. And I also know these distances. I know that X is 5, and I know that Y is 12. And so what am I trying to find? The rate at which the straight line distance between the cars is changing. So I'm going to call this S. It doesn't matter what you call it, as long as you're consistent. And so I am trying to find the rate of change of that distance, so ds dt. Now I need a formula that relates all of these together, and that would be
the Pythagorean theorem.
Indeed it is.
Oh, really?
Yes. X squared plus Y squared equals S squared. And so now I'm going to differentiate with respect to time. So the derivative of X squared would be 2x dx dt. And the derivative of Y squared would be 2y dy dt. And the derivative of S squared would be 2s ds dt. And now I don't know about you, but sometimes my life can be complicated. So I need to simplify it. So I'm going to divide everything by 2, and my 2's go away. And now that I have differentiated, I can plug in what I know. X is 5. Dx dt is negative 36. Y is 12. Dy dt is negative 50. And uh-oh, I have 2 missing variables. It's okay if I'm missing ds dt because that's what I'm looking for, but what is S? Oh, I can find it. It's a Pythagorean triple, right? A 5, 12, 13 triangle. Zach is just on a roll today, right? So look, 25 plus 144 equals 169, and we're taking the square root of that, which is 13. So I've got 13 ds dt. Now take your little calculators and let's solve for ds dt. Oh, my bad. I stand corrected. The human calculator, Jackson.
Mental math right here.
Whoa, crank out an answer. What we got? Let's put some units on there. -60 miles per hour. And does this make sense? And should it be negative in the context of this problem? Is the distance between the two cars decreasing or increasing? Well, it's decreasing, obviously, because the two cars are approaching the same point. Therefore, the distance between them should be decreasing.